right, people on YouTube, there is a quiz. Please do the quiz.
Yeah.
All right. So, all right. The correct answer, I'm gonna be annoying and I'm gonna mute myself and I'm just gonna tell it to the class here. Okay. Okay, all right. Here's the plan for the rest of the course. By the way, okay, I should say, okay, I'm not, okay, I'll repeat for the record what I just said is that DFS and BFS have approximately the same complexity because basically every iteration prints a node of the graph. There is the same number of nodes in the graph, whether you're doing DFS or BFS, and that means that their complexity is approximately the same. Of course, kind of if I didn't specify whether kind of with the best implementation, you could imagine like less and more efficient implementations of DFS and BFS. So for the rest of the course, what I want to do is I want to talk first about kind of something that was left over from before, which is recursive depth first search. So that's just the same algorithm, but implemented recursively. I want to talk a little bit about examples of graph search, specifically as relates to developing algorithms for things that might not seem at first like they're graph problems. I am then going to talk about implementing DFS without recursion, which technically we've already done, but I'm going to talk about that in a context which maybe would be surprising. So that's basically the plan for today, maybe tomorrow a little bit. We'll see depending on how fast we go. So we also have a few kind of self-contained topics, which are just like, here's an algorithm for this, here's an algorithm for that. And the job of those is twofold. So one, just to provide an example for something to implement in C. And another, those happen to be the algorithms that underlie the data structures in Python that work really well. So basically, like knowing about them is basically knowing about how computers work. So that's important in that way. So we then have kind of two algorithms that I really want to cover. We'll see if there is time, and that's Dijkstra's algorithm and a star search. And one way is they kind of wrap the course nicely in the sense that they use all those different aspects of 190 to accomplish something cool and non-trivial. So I hope you'll get to see that. So, okay, so that's the plan. And again, what should you get out of any of that? So we're moving to kind of the more complex parts of the course, similarly to how the end of 180 was maybe more complex than the beginning, where you were just kind of learning the pieces, still not really working on how to put the pieces together in a complicated way. So kind of on one level, like if it's a named algorithm, and knowing about it is just knowing about how things work. So that's important in that way. It's sometimes possible to ask a problem, or sometimes a problem comes up in life where you can like change up a small part of the algorithm in order to solve a new problem. So understanding the components and how they fit together and why they're there is important. And then at the same time, we're going to do some C implementations, and those you can just treat as examples of like, here's a complicated thing that I would implement in C. Okay. Let me see if there is anything on Discord that's interesting. Fascinating. Okay. So, okay, all right. So, sorry. So I wanted to do the recursive depth first search first. So I think it's been a while, although you are supposed to have implemented all of that in the lab this week. But just to remind you, so we have so sometimes we'll say traversal, sometimes search. So traversal just means get me all the nodes in the graph. Search means go through all the nodes in the graph until you find the right one. So in a sense, that's the same thing. Search for a node that doesn't exist is the same as traversal, because you have to go through the entire graph before you know that you didn't find the thing you were looking for. All right, but so people don't say BFT a lot. People say BFS, even if they mean traversal. Anyway, so what we're trying to do is we're trying to get through the entire graph by starting in kind of one of the starting points. And the way we're doing it is we're saying, okay, like we'll first look at the nodes that are connected to the starting node. So we'll look at 3 and 6, and then we'll look at the nodes that are connected to the 3 and the 6. So that means that we'll look at the 2, the 4, and the 5. So this graph is pretty small, so that's pretty much it. So the way this is implemented is you say, okay, I visit the first node, I visit 1, for example, and then I add the neighbors of 1 to the queue. So I add 3 and 6 to the queue. 3 and 6 are waiting to be explored. I take one of the nodes from the queue. So for example, I take 6 from the queue, and then I add the neighbors of 6 to the queue. So in this case, only 5 gets added to the queue. And I keep doing it, right? So I keep visiting a node, adding its neighbors to the queue, and then taking a new node out of the queue. So the first one that's in line and exploring that, adding its neighbors to the queue as well. Does that make sense? So that's BFS. So, sorry. So DFS is implementationally, it looks very much the same, but you just swap out the queue for a stack. So that means that when you visit a node, like you visit 6 or something, you add the neighbor of 6 to the stack now. So you add 5 to the stack, and then because the stack is last in, first out, that means that the thing that got added to the stack last, that's the thing that's going to get explored next. Right? So whereas before you were exploring it like 1, and then the things that are distance 1 from 1, so 6 and 3, and then the neighbors of 6 and 3, what you would do here is you would explore 1, and then maybe 6, and then 5. Like you try to go as far away from 1 as possible, as soon as possible. And the way that's accomplished is you visit a node, you add its neighbors to the stack, and the neighbors get explored right away, because the thing that got added last to the stack is the thing that gets explored first. Make sense? So that's DFS and BFS. So BFS is actually not super easy to implement. Am I not sharing my screen? So why did no one complain at least? Oh, they did, but in a different. Oh, they didn't. They didn't care. Okay. So the good news is that this was all reviewed. Implementing breadth first search traversal is actually not trivial with recursion. But if you think about it, depth first traversal is very natural, a very natural candidate for recursion, right? So what we're saying is, okay, if I want to do DFS starting from node 1, what would I do? I would just say, well, like DFS3, DFS6. And then if I'm at DFS6, I'm going to say DFS5. And if I'm at DFS5, I'm going to say DFS4 and then DFS2. And that's the same thing, right? So if you start with 1, you're visiting 1, and then you're saying, in turn, I'm going to call DFS on the neighbors of 1. So initially, what's going to happen is you're going to call one of DFS6 or DFS3. Let's say you call DFS6. So your traversal is 1, 6. So then inside DFS6, you're going to say DFS5. So 5 gets visited next. And then inside DFS5, you're going to say DFS4. So 4 gets visited next. Then you're going to do DFS3. After that, you're going so I suppose you'll get to DFS2. Right? So it's, again, because like right away, you call DFS1 and 1 gets visited, and right away, DFS6 gets called. So now 6 is going to get visited. And then what's happening in DFS6? Well, 6 is visited, and then DFS5 is called. So again, you're going as far away as possible from the initial node. Yeah.
This requires also
well, so here it's kind of it depends on how you implement it, right? So several, you've done actually several things, I think, in the lab, right? So one thing you can do is, yes, you can have a set of visited nodes to which you add. You can also have, like in question 2 from the lab, an array. That would be another data structure. However, if you have just nodes connected with edges, like just kind of a linked structure, then what you could do is inside the node, you can say, you can have a variable that says visited. Say, yeah. So depends on the implementation. All right, does that make sense? All right. So that's like that. So what I want to talk about now is kind of something that's very related but might look different at first. And that's kind of going back to game trees. So as a reminder, so we have this race to 21 game, right? So we start with 0, and then the allowed moves are +1, +2. And then the first person who gets to 21 is the one who wins, right? So, okay. So let's say that what I want to do is I want to enumerate all the possible games of race to 21, right? So what I mean by that So what I mean by that is, like, one possible game is I start with 0, and then we get to a 1, and then another person plays 3, and then another person plays 4, and then another person plays 6, and so on until we get to 21. And then another possible game is like this, right? And I want to try to enumerate all of them. So meaning print all of them, right? So the approach that we take here is similar to enumerating all passwords. So what I'll do is, let me copy and paste this. So what I do is I say, okay, so the prefix is the game that's been played up to now. And the score is the current score. And the path is all the possible games. Paths, and it's going to be clear why I'm calling it paths. Right? So the prefix is just the game up to now. So like, you know, like ones and twos and stuff. And then I'm saying, okay, if the score is 21, then the prefix is the only game that can be played because the game is done. If the prefix is something like, so whatever, so that's like, that does not add up to 21, then there are possibilities, right? Then one possible continuation is whatever, 2 to 1, and then another possible continuation is this, but 1 to 1 or whatever. Right? So what I'm saying is, okay, like if the score is 21, I'm done, and I'm just adding the prefix, which is a completed game, to the path. Otherwise, I'm saying, okay, enumerate all the games with prefix plus the 1 and with score incremented by 1, and also do that with prefix plus the string 2. Does that make sense? So let's do kind of a real game. Maybe that would make more sense. So let's say that I do like 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 18. So let's say that this is the prefix. And that means that the score is 18. So calling enum all with this prefix path. So what I want it to be is I want path to be so 2, 2, 2, 2, so 18 and then 1, 2. And also the same thing, but 2, 1. Right? That's the output that I want. Those are the possible things that could happen. In fact, with here, it's possible that it's going to be 2, 2 because that's allowed with 20. And similarly, I can actually also complete it with like 1, 1, 1, 1, 1, and so on. That's too many, like this. Okay. So that's the kind of thing that I want here. So the way I accomplish it is I'm saying if the score is already 21, that's it. The prefix is the only possible game. If the score is less than 21, then I'll call enum all on the expanded prefix with 1 and on the expanded prefix with 2. Does that make sense? Questions? Yeah. Say again?
It's strictly like it's the alternate is greater than. It doesn't end up being like it's
yeah. So you can get to 22 from 20. Yeah, that's a lot. Say again?
Person who played that last two.
Whatever you want. It's like it doesn't say here whether overshooting is like winning or losing. I suppose it makes sense to say that overshooting is winning because you can always if you can overshoot, you can also get to 21. But like it doesn't say here, right? So here it just says that the game ends when you get to more than 21. You could also just be like more fussy about it and say like, if it's 20, you're only allowed to do +1 and not +2. Okay, does this roughly make sense? So that's the same as just enumerating all strings, basically. But another way of looking at it is by thinking about this as what's called a game tree. So we briefly mentioned that in ESC190. A tree is just a kind of graph, right? So it's a bunch of nodes that are connected. So you can think of it as the game starts at 0, and then it could go to 2, or it could go to 1. And then from 2, it could go to 4, or it could go to 3. And from 1, it could go to 2, or it could go to 3, and so on. Does that make sense? So you could then say, well, like this is a graph. So it's a special kind of graph, but it's a graph. And I can think of just traversing this graph. And actually, a traversal of this graph, if you do it right, is going to correspond to a game. Right? Because what does DFS mean on this kind of graph if you start from 0? Well, it means explore this guy, and then explore this guy, and then explore this guy, and so on until you get to the end. And then once you get to the end, back up a little bit and explore the other direction here. Try to get as far away from 0. Right? So that's the same as trying all the possible games. So the first possible game is just, go left, go left, go left, go left, go left until the end. And then the second possible game is when you get to the end, let's say that we're playing to like whatever 5 and not 21. So let's say that this is the end, back up 1 space and go here. That is what DFS does, because when you're saying DFS 4, what it's saying is explore 4 and then DFS 5 or like DFS 6, DFS 5. Right? So that's the same as 0, 2, 4, 6. If 6 is the end, back up and now do 5 over here. Yeah. Well, so like the fact that the graph is directed just means that, so like you could have like a game like chess where it's still of course directed, but you could imagine drawing it as if like you're allowed to go back, because like you're allowed to take things back, right? But in general it doesn't. So if the graph is not directed, then in principle kind of it's harder to think about it as traversing it, because you could in principle like go back and forth. But that's fixable as well. So, all right. So if we think about it like that, then what we can do is we can do a depth first search traversal of this graph, this tree, and also get all the games. And this is how you might do it. So we'll have our stack. So the stack is going to have the prefix and the score, similarly to before, right? And then we'll just keep going while the stack is not empty. So get a prefix score pair from the stack. And if it happens that the score is greater or equal than 21, we're done and we're appending the prefix to the path. If not, then we're saying, okay, look at the neighbors of the prefix. What are the neighbors of the prefix? It's the prefix plus 1 and the prefix plus 2. Right? Because like what are the neighbors of 2? Well, they're 4 and 3. So like 2 plus 2 and 2 plus 1 are the neighbors. Yeah.
This is just the DFS.
No.
Because we're for.
Because it's a stack.
Oh, okay.
Okay, so like basically the structure of BFS and DFS is the same. It's just that with a DFS it's a stack. The problem with the BFS, so the reason it makes sense with a DFS but not as much with a BFS here is that is that basically like we want the order of things to be kind of a continuous path in the graph. We do not want to back up in the middle, which BFS does. All right. So let's do that again. So what I'm doing here is kind of similar in structure to this, except I want to avoid recursion, right? So the job is still like the prefix is the game played up to now, and the score is the current score, and the path eventually should be just all the possible games paths, right? And so here what I'm doing is I'm saying initially I'll just put in the prefix and the current score, which was given to the function as input. So I'll just give it the empty prefix and a score of 0 as the start, if that's what I want to do. And then I'll keep right? So it's just DFS. So I keep like I visit a node, I add its neighbors to the stack, and then I get the next node to visit from the stack. That's all I'm doing. So, and I'm doing it while there's still stuff in the stack, right? So get a new pair from the stack. And if we're actually done, okay. And now I add the first neighbor, right? So I'm saying add this pair. So prefix +1, score +1. So explore that later. That's the same code as in the slides. So like I feel free to just press tab. And now append the second neighbor to the stack. And we return path over here. So if I want to call it, I'll say initially the prefix is 0 and the score is 0 and there's no paths. Make sense? So this turns out to be a general technique that you can use in order to convert basically anything recursive into an iterative algorithm, because essentially, so we're not probably going to have time to get into it in this course, but basically underneath what Python does when you do recursion is it also has a stack where it keeps track of the calls that it still has not done. Make sense? Questions? So again, like this I think is not an easy thing to get your head around. I think the way to think about it is this, like that's what we're doing. We keep adding the neighbors of the prefix to the stack and then exploring them. What's a neighbor of a prefix? Well, the neighbor of 2 is just like the possible game state that you could get to from 2, and that's either 4 or 3. right? So one important thing to note here is that there's no graph data structure that we're using really, right? So the graph is more in our heads for illustration. It's that we just know that the neighbor of 2 is 4 and 3. Make sense? All right. So that works kind of in all sorts of areas of life, like, for example, solving integrals. So if you think about it, like what does it mean to try to solve an integral? Well, you start with some expression, right? And then you have rules about how to transform this expression, and you have rules about when you're done, right? So like if you get to like whatever sine squared x, that's considered to be a solution because it doesn't have the funny integral sign in it. An arbitrary convention, by the way, like it's not as if you can compute sine squared of x without it calculated. So you can think about it as like there is like an integral here, and then the moves that you're allowed in the game are the various transformations that you can do, right? So like you can do like an integration by parts, or you can do like a trigonometric substitution, or you can do some funny algebra, or like sometimes an identity that you can use, and so on. Right? So you can think about kind of you trying to solve the integral as you basically exploring a graph and hoping to find a node where that node would be considered a solution. Right? And like, I think it's a little bit useful to think about it this way, although opinions might vary, but you can think about different strategies to do this that are kind of analogous to depth first search or breadth first search, where you might say, one possible strategy is I have my initial expression and I'll try all the possible tools that I have to transform it once. Right? So I'll try some integration by parts. Well, whatever I get, that's what I get. I'll try all the possible substitutions I can do. Whatever I get, that's what I get. And then I'll try all the neighbors of the transformed expressions. And then I'll try all their neighbors and so on. Or you could have something like, well, I'll try a transformation that actually seems promising to me. And then, well, even though that's not the final solution, I think that's kind of on the way there. So I'll try another possible transformation of that, and then a transformation of that, and so on. And that would be kind of more analogous to depth first search. Right? Because ideally what you want is you want to just like start here and then go here and then go here, and that's it, without trying integration by parts here or integration by parts here. Right? So what makes sense in life? Like what do you do in calculus? Do you do like breadth first search or depth first search? Whatever works. So like, I think kind of the correct answer is like, you shouldn't, like, neither actually makes that much sense on its own. You need to also have some kind of intuition about what seems promising. And sometimes your intuition is imperfect, right? So the way it actually works is you say, okay, like, this looks like the kind of thing on which substitution will work, and then you try it. And then if it seems like you're close, then you keep kind of trying to push ahead. If it seems not promising, you try something else. So in practice, it's a kind of a mix of depth first and breadth search and breadth first, together with some kind of intuition for what's promising and what's not. And there is a way to formalize that as well. One of the ways to formalize it is A star, which is why I really want to tell you about A star. Unfortunately, in order to implement A star, we need priority queues. And in order to implement priority queues, we need heaps. So that will have to wait until probably like next Thursday. But I think it's like worth looking forward to. So I have 10 more minutes. So are there questions about anything? All right. Let me see if there is stuff on Discord. Yeah. Okay, that's a good question. So like, why are we doing and it was answered, it was a good answer, but I think it's worth answering again. Like, why does while stack make sense? So basically we keep adding neighbors here, and the way we keep adding neighbors is we say if the score of the current prefix is smaller than 21, then we'll add more neighbors. If not, then not. So that means that if we have prefixes that still need to be expanded, the stack will keep growing because we visit a prefix that still needs to be expanded, and right away we append more stuff to the stack. On the other hand, when we start running out of prefixes that need to be explored, the stack will eventually become empty, because if the score is greater than 21, you just continue and you just popped from the stack. So the stack shrunk by 1 and it did not grow to compensate over here. So once you get to just nodes that have scores of 21, the stack will become empty, and that's because you will have explored the entire graph. Make sense? All right, so I am a little bit ahead of where I want to be, which is great because globally speaking, I'm a little bit behind of where I want to be. So we'll start a new topic for the last 8 minutes. And that's going to be priority queues. So a priority queue is an ADT. And it has the operations insert, and pop. So it's basically like a queue, except everyone has a priority, and the person who gets out of the queue first is the person with the highest priority. And sometimes that's implemented as like numerically priority is as small as possible, sometimes as high as possible. Whatever. So the default Python one is like lowest numerically, so that's what we'll do. So for example, you might say like insert ESC190, oh well, like, okay, 195, and the priority for that is going to be 5, and then we'll insert 195, and then civ102, and that's 10. So remember, priority lower is first, right? And then we'll insert ESC195, 190, and the priority will be 0. And then it's an example. And then pop. So that would get you ESC190 first. And then if you pop again, that would get you ESC195. And then pop again, that would get you civ102. Make sense? So that's what we want to do. We want to be able to give a priority, and we want to get the elements from the queue in order of priority. So why might you like to do this? So the answer for the purposes of this course is A star. But you might imagine kind of doing a simulation of patients in a hospital or something, and like you're right, so similar to how we did kind of a simulation in project one of ESC180, you might just like to run the simulation in order to understand kind of how long the lines in the hospital are, what like is the wait time, stuff like that. And you would like generate fake patients with different priorities, and then you would treat them in order of priority. That is how it actually kind of works in the emergency room. And you might get like, if you run the simulation with a lot of fake patients, you might get some insights about how to organize the hospital queuing system or something. So that's kind of one reason that you would do this. Now, you would not really need an ADT for that, because like you don't really care about efficiency so much when you're doing this kind of thing. When we're doing a star, we really will care about the efficiency of the implementation here. Yeah.
Is copy always done for the object of the lowest priority or the highest priority?
Well, it's the highest priority, but the convention, unfortunately, is that, and that's a convention, like you can change it, is that highest priority means the lowest number. But you could change it. Of course, it's like just a matter of like changing a sign. So, okay. So let's implement something inefficient for this. That's not really difficult. So we'll do like class priority queue. So we'll just do, yeah, so Copilot is thinking what I'm thinking. So I'll just say, okay, initially the queue is just going to be empty. And then what we'll do is we'll make the list be something like this, right? It's going to be like whatever. So that should be the quotes. So like ESC190. And then ESC195.5, Sev102.10, stuff like that. And we'll just keep it sorted. So that means that it would be more convenient to do it like this. And then pop would just be take the first element. Right. Okay. So insert would look like this. So we just append the tuple priority value, and then we just sort. Right. So not super efficient. So we spend n log n time doing each insert. But pop is going to be efficient, because all pop is going to do is it's going to pop element number 0 and then get me the value. So in this case, insert would be O of n log n. And pop would be O of 1. Make sense? Yeah.
Can you insert? Could you just go through the list?
Yeah, totally. So the suggestion here is, instead of doing this, so that would be all of it. The thing is, that's still not very efficient. So like the reason I didn't bother is that that's still much less efficient than what you can do with a heap. So with a heap, you can do both in O of log n, which we'll hopefully see later. All right. Other questions? Yeah.
Is it necessary? Is a priority queue, does priority queue have to be sorted or anything?
So it does not have to be sorted. So kind of all the ADT has to do is it has to keep the rules of what insert means and what pop means. So the implementation is up to you. And like you saw, there's kind of two variants of an implementation already that we saw. In fact, the actually efficient implementation, it's like neither sorted nor not sorted. It's not even a list that's that you keep. Well, it's kind of the list that you keep the thing in, but it's not exactly sorted. It's arranged in such a way that you can retrieve really quickly. So yeah. All right. Other questions? All right. Thanks everyone for coming. Bring your friends tomorrow. I'll see you there. Bye.